But there's also something more about seeds and sex between trees. Some species of trees do not produce their seed every year. It's like wine. There are some good years and some bad years. We find years with a lot of pollen and seeds being produced, and other years with hardly no seeds that we can find on the ground. How can that be? How can be successful a strategy by which you don't maximize your reproductive output? Actually, the explanation of this lies in the connection between trees and animals, especially the seed predators, those who like eating fruits and seeds. If you live in a place, if you share your place with many seed predators, you have to be careful, because all or most of your seeds risk to be eaten up. So what's the solution? Well, you go for a number of years without producing a lot of seeds. The population of seed predators then crash down, obeying the law of prey and predators. There's not a lot of food, so you cannot afford a very large population. After a number of years, when the populations of seed predators have gone down, then all of a sudden you produce a lot of seeds because the predators are few, and then there's high likelihood that some of these seeds at least will escape predation and be able to grow a new plant. Now the question is, how do trees decide what is the right year to produce a lot of seeds? And this is also a result of evolution and natural selection. Usually, the best year to produce seeds is the year when these seeds would find very good conditions for germinating. This means a lot of light, not a lot of competition by ground vegetation such as herb or shrubs. When are these conditions coming? When something happens to a forest. Some kind of disturbance that opens up the gap that we were talking about just a short while ago. A fire, for example, a windstorm, some sort of damage that brings some trees down, opening up light and resources for the seeds to germinate. And this is in fact what we see. The best year in which trees decide to produce a lot of seeds are also the ones with high likelihood of forest damage. For example, the year of a drought, when it's more likely for a fire to spread. This is just another example of the amazing connections between the trees and their environment, and the ways in which trees, just like any other living being, are able to perceive what happens around them and adapt their behavior. I have just found another example of amazing relationships between things that live in a forest. Come with me, I'll show you. On some of these pine trees, we find a different plant. We can follow its stem, climbing up along the stem of the pine, and we can recognize it from the leaves. This is ivy. Ivy is what is called an epiphytic plant. It means a plant that uses another plant to grow on. Ivy does not have roots. The stem does not end up in roots, it just ends up in the soil. The roots of the ivy are found on the branches. These are small roots that the ivy uses to get attached to the main stem that it grows on. But why do some pine trees have ivy while others do not? Well, some people believe that ivy is actually damaging the trees, maybe by sucking the sap that flows just below the bark, maybe by shading up the leaves, and preventing them from carrying out photosynthesis correctly. In fact, it's not uncommon to see ivy growing up on dead trees, such as this pine over here. But actually, the process is the other way around. Ivy does not suck up sap, does not shade up the leaves. It merely lives on some host trees. It doesn't do any damage. But of course it has green leaves. It wants to photosynthesize as well. So it grows much more likely on trees that allow more light to get through. And dead trees are a perfect host, because there's a lot of light that comes through their dead canopy. So if you see ivy on a tree, don't kill it. It's actually a consequence of some interesting biological process. A connection between our sun, the trees in the forest, and the other living beings that populate it. Forests also hold another secret. The secret is in the soil. The soil of the forest is made of a very specific material that cannot be found in any other ecosystem. This is humus, or organic matter. The soil in the forest lives in a perfect equilibrium with the trees above. The trees let fall parts of themselves that are not needed anymore, such as pine needles here, fragments of bark, dry leaves, small part of branches. This material accumulates on the ground, but this is not wasted. In a perfect circular flow, this is the preferred food for things that live in the terrain. Decomposers, mostly fungi and bacteria, so small that we cannot see them, but we can smell their effect. We can smell the odor of earth. We can smell fungi sometimes, because in fact fungi is what keep all these material together. They start decomposing the litter that falls down from the trees, and they grow their own tissue within it. This is called mycelium, is the growing body of fungi. The part that we usually think about when we think of fungi is the reproductive part, the part that is responsible for the formation of spores and the sexual reproduction of fungi. But the body of the fungus is the mycelium here. And the mycelium wraps up the soil as in a web, a very large web, in fact, which can also connect trees to one another. The mycelium resembles small roots of a plant, and it can actually take on a symbiosis with the plant roots, extending the root surface, allowing the tree to absorb more nutrients and even to communicate between themselves. Recent discovery in forest science in fact demonstrate that the mycelium of the fungi is like a wood wide web in the forest soil, by which trees are able to exchange information, nutrients, and alarm signals. When an insect comes that threatens the leaf of a tree, it has been found out this tree produces some chemical substances that are then sent around to the neighboring trees by traveling in the fungi highway. The neighboring trees learn about the threat and try to adapt to it, for example, by synthesizing repellent substances that make the life of the insects harder and makes it harder to attack the leaf of the tree. And we are just beginning to discover the function, all the function and the processes that happen in the forest soil. That also, for example, is the main store of carbon in the forest. We need trees to suck up carbon from the air, especially as we are emitting excess CO2 by the day. But what we don't usually think is that the largest store of carbon in a forest is not in the trees. It is in the deep soil, in all the organic matter, often several centimeters or even 1 meter deep, that contains all the carbon. It is able to store it for a very long time. There is a very special place where we can notice the growth and the change of trees. This place are the tree rings. Every tree, at least in temperate latitudes, goes through a change in its growth pattern throughout the year. In the spring, when it has a lot of light and a lot of water, it produces a light wood with large cells with a thin cell wall. At the end of the summer, when the temperatures begin to drop and the light begins to dwindle, they can still produce wood, but the wood is very different. It's made by very small cell with a very thick cell wall. This determines what we know as tree rings. Narrow bands that alternate light and dark colored cells, the spring wood and the autumn wood. And everyone knows that by counting the tree rings, we can know the age of the tree. Let's try and make an exercise here. This pine was cut probably 5 or 10 years ago, and I will now try to count its rings. The tree has about 80 rings that I can see, so we can be quite sure that when it was cut, this tree was 80 years old. Not a very old age for a pine tree. There were probably a reason for cutting it down. For example, maybe it was dangerous. We are very close to the road here. It had died for some reason. We can see some insect entrance holes here. So maybe it was colonized by a parasite. Or maybe it was just to make room for other trees around it to grow better. Something that we know as thinning the forest. But the tree rings do not only tell us about the age of the tree. They tell us a lot of different stories. By looking, for example, to the width of each tree ring, we can reconstruct the growing conditions that occurred in the year that the ring was formed. Large ring, very good growing conditions. Hot temperature, plenty of water, a lot of nutrients, no stress. Narrow ring, stressful conditions. A frost maybe, or a drought. Some damage by fire or insect, or a very cold season. By reconstructing the series of width of each tree ring, the tree works as a living diary of the environmental conditions of the last century. And the oldest living trees in the world have been used precisely for this reason, for reconstructing the climate far, far back in time, up to 5,000 years ago, when there were no thermometers nor humans to measure temperature. And they were the key in understanding that something is happening called climate change. Trees and humans have a lot more in common than we think. For one thing, tree cells have to survive and be kept alive by the same very mechanism that keeps our cells alive, by consuming oxygen and energy in the form of carbon products. In fact, trees do not only produce oxygen with photosynthesis, they also consume oxygen and glucose and sugar in order to maintain their cells alive. This is what is called cellular respiration, or self-breeding. And this is also a reason why trees can be stressed out in difficult environmental conditions. One of the most common of these conditions is drought. When a drought hits, photosynthesis is much harder to carry out because the water that is needed to photosynthesize is not enough. The tree so slows down its physiological activity in the attempt to save water. But by shutting down photosynthesis, it also interrupts the provision of sugar and glucose to its cells. If the drought lasts too much, the tree does not have the sugars it needs to be kept alive anymore. Something then happens. As a symptom of this stress, the tree tries to react. One way of reacting to extreme drought is letting go of whatever can cause you to lose water. The pine tree behind me is heavily defoliated. It has let go of most of its leaves in the past 1 or 2 years as a likely response to intense drought, in a last attempt to save some water and avoid losing it by evaporation after photosynthesis. Some tree can recover from this kind of damage by growing new leaf the next year, if the drought stops and if the tree has enough water and energy again to reform completely its crown and its leaves. The tree ring form in this here will be, of course, very narrow, because the tree won't have had all the energy it needs to form enough wood. Some other trees cannot recover from this kind of damage if it lasts too long, and in fact they become weakened and they are more easily attacked by secondary agents, insects, fungi, parasites that find it much easier to colonize a tree if it is stressed out, because the stress also lowers the innate resistance to these kind of agents. Obviously, drought is made more frequent and more intense by man-made climate change, and this is why in forests of the world we are increasingly seeing dieback waves, mortality episodes that are widespread into global forest. And they can happen not on one species only, but they can involve tens of different species at the same time, threatening the continuation of the forest and the benefits that it gives us. But why are forests important? Well, some things have already surfaced in this walk in the woods. For one, the trees suck up carbon dioxide, and so they help us in fighting against climate change by removing a part of the greenhouse gases that we unfortunately still emit in excess. But these roots over here, these exposed roots of a pine tree, also tell us a different story. The trees are able to protect us and make us more resilient in times of change. The roots of a tree, although we seldom see them, so we seldom think about them, are able to break down rock. They hold the soil together. They attach to the soil and they prevent the soil from slipping down. For example, when it rains a lot, they can be very important in preventing landslide and hydrological danger. This is a rare case in which tree roots are exposed that allow us to see how much developed a tree root system often is. When we see a tree, we must think of it as having, in fact, two crowns. One above ground and one upside down below ground. Such is the extent of tree roots. In a forest, therefore, there is always a network of roots keeping the soil together, working for us by keeping us safe. This is one of the benefits of the forest. What we call ecosystem services, or gifts, if you want, that ecosystem by their own functioning make us. But forests actually are rich of services and benefits to mankind. The most traditional one, but one that we still need, is wood. A clean, renewable, biological material. By using wood wisely, we can also find solutions to the problem of climate change. Wood retains carbon for a long time, even after the death of the tree it comes from. If we use wood for long-lived products, such as pieces of furniture, flooring, construction material, we are keeping carbon stored in our buildings, in our homes. We are surrounded by small safes for carbon that can last for a very long time, preventing this carbon to entering back into the atmosphere. Also, by using wood in construction, we can avoid producing other materials that are much worse for the climate, because they imply a large quantity of CO2 emissions for their making, for their production, such as steel or cement. And obtaining wood from the forest is not in contrast with the conservation and the continuation of the forest and its functioning. By applying what is called sustainable forest management, we can know the speed by which trees grow every year. The most important thing is that we keep and we take wood at a speed that is lower than the natural speed of growth. By this way, we make sure that the resource is renewable, the forest is not impoverished, does not disappear, but continues to live. We have come at the end of our walk. We have walked in the forest to learn about its functioning, to learn about how trees are connected to each other. They are connected to the environmental elements, to wind, to light, even to fire. They find solutions for living while staying in the same place. They entertain relationships with one another, with animals, with the soil, with other plants in this wonderful ecosystem. And all this is also connected through us, through the benefits that forests give us every moment of our life. They suck up carbon from the air, they give us a clean and renewable material. They are a place where we can have a walk and recover our health and our spirit. They protect us from landslide and from hydrological dangers. They are, in fact, a gift for each of us. In every moment, every tree on this planet is doing something for us, even if it's very far from where we live. How do we then experience the connection with the forest and with the ecosystem? How can we perceive that we are deeply intertwined with the fate of our forest? By using, in my opinion, our senses. By feeling the heat of the sun that's warming me up right now. by smelling the soil and appreciating the richness of life that is occurring within it, even in this very moment. By listening to the sound of birds that are waking up to spring and which have made us company throughout this walk. By touching the bark of the trees, the leaf, experiencing the life that goes on through gas exchange, photosynthesis, and respiration in every part of these wonderful living beings. Thanks for being with me in this walk. I hope to have provided some inspiration for the course that you're about to attend. Have a nice day. Goodbye.